All right, this is Algebra 2, Lesson 55. We're going to talk about finding probability. If I can basically, even before we start, take this entire lesson and give you like one major thing, this is what I want you to know, and we'll see it later on in the notes. But probability is the number of desired total over, completely messed that up. The number of desired over the number total. Okay, number of desired over number total. Number of desired over number total. Class, what is probability? Okay, let's do that a little bit better this time. Class, what is probability? Okay, great. That's a lot better. Okay, so let's say that I am flipping a coin and I want it to be heads, right? I'm on the, I'm captain of the football team. We're doing a coin toss, right? The ref is flipping the coin, and I call what? Okay, let's say heads. All right, how many of the possibilities are desired? One. No. Why one? Because there's only one head. Okay? There's only one head. How many total possibilities are there? Two. So the probability as a fraction is 1 over 2. Right? So the probability of getting a head on a coin flip is 1/2 or 50%. Okay? Right? As a fraction, yes, I understand the concept of 50-50, but 50-50 is not probability. 50-50 is odds. Okay? And there's a difference between odds and probability. Okay? Because probability is desired number over total, right? And that gave me that 1 over 1, right? Or sorry, 1 over 2. Okay, odds, okay, is desired over undesired. It's a little different here, okay? Which means there's one that's desired and another one that isn't desired, right? So it's really 1 over 1. 50 over 50 is 1, right? Okay? So you need to understand the difference between probability and odds because it's going to change how you set it up. So all right, so let's go into this. An event is an outcome or set of outcomes of a sample space. The probability of an event is the likelihood of that event occurring. Okay, like winning the lottery. What's the probability of winning the lottery? It's very, very small. But those are numbers that we can discover and find out. Okay, it is given as a number on a continuous scale from 0 to 1. Okay, where 0 means that the event is impossible. Okay, so if there was 0 desired numbers, right, that would be 0 over a number, and 0 divided by anything is 0, right? So our smallest probability is 0, going all the way up to 1. Okay, meaning that it's a guarantee, 100% probability of it happening. Now, understand when we said 50-50 and we got 1 over 1 and that's our 1, we're not talking about probability there, right? We're talking about odds, a 1-to-1 probability, okay? But if let's say our number desired, let's say that I'm going to flip a coin and I want either a heads or a tails, right? So how many are desired? 2. And how many total options are there? And what's 2 divided by 2? 1. And what is 1 as a percent? 100%. Right? Which means I'm going to get what I'm looking for. There is 0 chance. I'm not going to. The only thing that could happen is if it landed, and I guess sometimes this rarely happens, but it does happen, is where it stays on its side. Right? Okay, but we're going to count that out and say, if I flip a coin and I want either a heads or a tails, I have 100% of getting what I'm looking for, right? Okay? All right. Probabilities can be written as fractions. All right, let me go back to this, where 0 means that the event is impossible and 1 means that the event will definitely occur. Probabilities can be written as fractions. They can be written as decimals. They can be written as percents. So for an event, that is just as likely to occur as not occur. The probability is 1 to 2, like in our coin flip. Shown as a percent is 0.5. Shown, or sorry, as a decimal is 0.5. As a percent is 50%. Questions, comments, concerns up to this point? Understand everything? Great. Let's move on here. Probability experiment. That's an occurrence whose outcome is uncertain. An event in a probability experiment can also be called a random event because it occurs at random or by chance. For example, the event of getting heads in the experiment of flipping a coin is a random event because it cannot be predicted. Okay, we know what the probability is, but until we actually do it and get the results, do we know for certain what's going to happen? No. Okay, it's an experiment. We know what is desired, we know what the options are, but until we have flipped the coin and it's landed and we can see what it is, it's still theoretical. Okay, which is why we see theoretical probability listed here. Okay? All right, so for equally likely outcomes, the probability P, okay, P is standing for probability of an event occurring, is the ratio, is meaning equals, is or equals the ratio of the number of favorable outcomes to the total number of outcomes in the sample space. That's just what I told you on the other page. Probability is desired over total, okay? Where a favorable outcome is an outcome in the event, okay? So we can start to look at different things. We don't have to flip a coin. We could roll a dice or a die, right, where it's numbered 1 through 6 and it's even. It's a fair die. It's not loaded or weighted, right? What is the probability of rolling a 1 whenever I roll a die? 1/6, right? Because 1 is what's desired. There's 6 total options, right? We could change that up and say, what's the probability of rolling an even number? 1/2, because there's 2, 4, and 6. There's 3 desired. There's 6 total options. 3 over 6 can be reduced down to 1/2 or 50%, right? Are we seeing how that works? Okay, we could roll 2 dice and we would get something else, right? All right. All right, we want to notice in the formula that the outcomes must be equally likely in the experiment of rolling a number cube. The likelihood of rolling the 6 outcome is the same as rolling anything else. Okay, the probability of rolling an even number, as we've seen, is 3/6 or 1/2, because there are 3 favorable outcomes, 2, 4, and 6. Out of the 6, 1, 2, 3, 4, 5, 6. This probability is a theoretical probability because it should say this should happen. Okay, we haven't rolled the die yet. Okay, so theoretically my probability is 1/2. Okay, in theory, half of all the rolls should yield an even number, but actual experiment may yield different results. For instance, every time I flip a coin, right, I should get a heads, then a tails, then a heads, then a tails, then a heads, then a tails. But does it always happen that way? Even on a fair coin, is it possible to get heads, 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 heads? It's possible, right? Which would not meet our probability. It would break the probability, but it does happen. So until we flip the coin, our 50-50 chance is theoretical. Okay? Does this make sense? So here we're going to see something else. We're going to talk about dependent and independent events. Let's look at geometric probability, though. Geometric probability is a theoretical probability, meaning it hasn't happened yet. We haven't tested it, based upon geometric measurements such as length, area, or volume. For instance, we could, how many of you have done archery with Mrs. Dabney? Okay, several of you. All right, let's say that I know I'm going to hit the target, but we're dealing with hitting the bullseye as a matter of probability. Okay, we would take the area of the very center of the target. That would be my desired outcome, right? That would be my number of desired over the area of the whole target. Okay, and I could find out what the probability of hitting the center of the target would be, right? If I knew I was going to hit the target, but I wanted to know what's the probability of hitting the center target, or I could pick different areas of it, right? Okay, and find out what that probability is. So do you see how we can use probability where it concerns area? Yeah? Okay, and we can do that same thing with volume, right? Length, those types of things. So when two events are independent, the occurrence of one event does not affect the probability of the other. When events are dependent, the occurrence of one event does affect the probability of the other. Let's say I had, gosh, I wish I had a deck here with me today. How many of you guys, I mean, you guys are familiar with a deck of cards, right? All right, how many cards are in a deck? 52 cards in a deck, and that excludes jokers, right? All right, so I've got 52 cards in a deck. All right, I come over to Diego. I say, Diego, what's the probability of you drawing a heart? Well, how many hearts are there in the deck? You don't know. How many are there? There's 52 hearts in the deck? There's 13 hearts. 13. So because, all right, because there's how many suits are there? 4. What's 52 divided by 4? 13, right? So there's 13 hearts, right? So his probability of drawing a heart is 13 out of 52, right? Which would reduce to 1/4, right? Because a fourth of the deck is hearts. All right? So let's say he draws a card, right? And then he puts it back, right? He looks at it and he puts it back. And I come over to Eric, right? And we want to know what Eric's probability of drawing a heart is. What's Eric's probability of drawing a heart? 1/4. Why? Because he put it back, right? So there's the same number of hearts and the same number of total cards in that deck, right? Those two events, are they dependent or independent from each other? Independent, right? Because what happened with Diego does not affect what happened to Eric, right? Because he put the card back. All right? So when we look at word problems, we're looking for the word replaced. We put it back. That is a big red flag that these two events are independent. Now, Diego draws a card and he keeps it, right? His probability was still what? 1/4. Okay? But Eric's probability is what? How many hearts are there? Or what's the possibility? The possibility, if he got a heart, is that how many hearts are left? 12. And how many total cards are left? 51. So he has a 12 out of 50. So if we're asking ourselves, what is the probability that Diego got a heart and Eric got a heart, we would see this. We would see 13 over 52 times 12 over 51. That would tell me what the probability of both of them getting a heart is. And we could change that up. We could say, what's the probability of getting a king, right? What's the probability of, getting a number between 1 and 4, right? We could find out all of those different scenarios. So this is example of dependent, meaning he didn't put it back. And independent is 13 out of 52 times 13 out of 52, right? Or 1/4 times 1/4. What's 1/4 times 1/4? All right, 1/16. So there, if he puts it back, there's a 1 in 16 chance that both of them got a heart, right? What is 13 over, that would be what, 1/4 times 12 over 51. Does anybody know what that comes out to? If Diego keeps the card, he doesn't put it back, what's our probability that both of them get a heart? 1 over 17? So it's not a big difference, but by him keeping that card, he's reduced Eric's probability, right? All right, this is how people count cards at casinos and things like that. It's all probability and odds, okay? Because the moment a card has been played, meaning it's missing from everybody else's hand or whatever. Does that make sense? Okay. Let's see. So this is how this looks. Is for independent events, it's probability of event A happening, which is where we saw right here, 1/4, times the probability of event B happening, which was still 1/4. All right, this is independent, what we see up here. Okay, which I guess I probably should have put on the board over here so that people watching the video can see it. So you're listening, independent for what we just talked about is 1/4 times 1/4 is 1/16, right? So probability of event A times the probability of event B. But when we talk about dependent events, we have 1/4 times 12 over 51. Right, and we got 1/17. Okay, now the way we show it here is for dependent events, it's the probability of event A, which we saw was 1/4, times the probability of event B divided by event A. Okay, but if you understand it, we don't really kind of have to go through necessarily that division process. Oh, I'm sorry, not necessarily B divided by A, but is the probability of event B happening given that A has already occurred, okay? Which is where we took one out of the desired and one out of the total, okay, and got the 12 out of 51. Okay, odds. We've talked about odds already, but odds are number of favorable outcomes over number of unfavorable outcomes, right? That's how we got in our coin flip 1 over 1. Okay, because one was desired over one that was undesired. Odds are sometimes written as the word 2 or with a colon, number of favorable outcomes to the number of unfavorable outcomes, where you see a colon show up here. So you might see the odds of them winning are 3-2, or 3-2, or 3 over 2. Okay? So that's how we would represent odds. Like ratios? Right. Yeah, it's the same thing as a ratio. But what you need to remember is that there's a difference in what those numbers mean in a probability versus an odd. Okay? Desired over undesired versus desired over total. Okay, a probability model shows the probability of each outcome in a sample space. The probabilities can be theoretical or experimental based upon actual data, things that have actually occurred. So if we kept flipping coins, we could write down our results. That would be experimental. Does that make sense? So we could sit down and find out, okay, what actually did happen. The sum of the probabilities in a probability model should sum to 1 or near 1 if rounding. Okay, some of the probabilities need to add up to 100%. Does that make sense? Okay. All right. Let's see if we have some questions here. I did not bring that up. Give me a second. Let's see, how much time do we have left? You guys are out of here at 36, right? So not really enough time to pull up that. Let's go to your questions. And why don't you give me one from your book? Something in your homework. How about B? Okay, estimate the probability the point chosen randomly inside the rectangle is in the shaded region. All right, so I'm going to draw a rectangle. You guys are going to help me out here a little bit. Okay, we see that this is shaded. Is it what? It's 7 here, 5 from here to here, and then 4 on the width, right? Okay. Okay. So probability of desired over undesired. So what we want is we want the area of the shaded region over the area of the whole rectangle, right? Well, what's the area of the whole rectangle? 28 inches squared, right? How did you get that? Okay, 4 times 7, length times width. All right, the next thing we need to do is find the area of the shaded region. Now, we can do that in one of two ways. One, we could see that this is a, the shaded region is a trapezoid, find the area of the trapezoid. Or we could find the area of the triangle and subtract the area of the triangle from the total area, right? All right, let's try that. Because we know this is a right triangle, what should this length right here be? If I know this length is 4 and this length is 5, does anybody 3, right? Because it's a Pythagorean triple, right? So we could use the Pythagorean theorem to solve for that, but for sake of time. All right, so we see 3 is taken out of that, which means the rest of this is 4, right? So now I have my trapezoid. Does anybody remember how to find the area of a trapezoid? Okay, so I would take that area. So what's 7 plus 4? 11. What's 11 times 4? What's 44 divided by 2? All right, so I should get 22 inches squared divided by 28 inches squared and reduce that fraction all the way down to, let's see, I get like 11/14. All right, so if you get 11/14 and then go ahead and get that decimal, it should come out to 0.79. It's your probability. Remember, we're not trying to solve an area here. We're trying to solve probability, so there's not a unit attached to that, okay? We would say, or you could say 79% chance, okay? All right. Thank you. We'll see you guys later.